Ever wondered how the moon was actually created? Imagine looking up at the night sky, where the moon, with its ethereal glow, has been a constant companion for eons. It's more than just a celestial body. It's a symbol of wonder, inspiration, and mystery. But have you ever paused to ponder its origins? The moon's creation story is a cosmic saga that blends cataclysmic events, scientific theories, and a dash of celestial poetry. It all began over 5 billion years ago, during the chaotic infancy of our solar system. At that time, the Earth itself was still forming, a molten, volatile world subjected to the constant bombardment of celestial debris. One such colossal collision, an event of unimaginable scale and violence, is believed to have given birth to our moon. This theory, known as the giant impact hypothesis, suggests that a Mars-sized body, often referred to as Theia, slammed into the young Earth with a force that defies comprehension. The aftermath of this titanic impact was a scene of cosmic chaos. The collision was so intense that it vaporized Theia and a significant portion of Earth's crust and mantle, ejecting a vast amount of debris into space. This debris, consisting of molten rock and vaporized elements, formed a vast glowing disk of material that orbited the Earth. Within this disk, gravity began its work, pulling the particles together, clumping them into larger and larger masses. Over time, these masses coalesced, giving birth to a nascent moon that gradually took shape. As it cooled and solidified, the moon settled into a stable orbit around the Earth, becoming the luminous satellite we see today. This cataclysmic birth not only forged the moon, but also reshaped the Earth, tilting its axis and setting the stage for the climatic conditions that would eventually allow life to flourish. Yet, the giant impact hypothesis is not the only explanation for the moon's origin. Over the years, scientists have proposed various theories, each painting a different picture of this celestial drama. Some have suggested that the moon formed simultaneously with the Earth, a twin planet born from the same primordial cloud of dust and gas. Others theorize that the moon was once a wandering body, a wayward celestial traveler, captured by Earth's gravity. However, these theories have their shortcomings, failing to account for the moon's unique characteristics, such as its size, composition, and the specific isotopic similarities it shares with Earth. The moon's story doesn't end with its formation. Throughout its history, it has been a witness and participant in the dynamic evolution of the Earth. Its gravitational pull stabilizes our planet's tilt, moderating the climate and contributing to the rhythms of life. The moon's phases have inspired cultures and calendars, its surface bearing the marks of countless impacts and geological activity that provide a record of the solar system's history. Even today, as we explore its surface and uncover its secrets, the moon continues to captivate our imagination, symbolizing the eternal dance of celestial bodies and the intricate web of forces that shape our universe. As we delve deeper into the mysteries of the moon, we uncover more about the story of our own planet and its place in the cosmos. The moon, with its serene beauty and silent presence, stands as a testament to the forces that sculpt worlds and create the conditions for life. Its creation story is a reminder of the violent yet awe-inspiring processes that give birth to celestial bodies and shape the universe. So, the next time you gaze at the moon, let your mind wander back to that momentous collision, that cosmic dance that led to the birth of our closest celestial neighbor. It's a story that spans billions of years, a story of destruction and creation, a story that continues to unfold as we strive to understand the mysteries of the universe. The early solar system. Let's rewind the clock to about 4.5 billion years ago, a time when our solar system was a tumultuous and nascent realm. Picture a vast, dark void scattered with swirling clouds of gas, dust, and ice, all remnants from the explosive death of earlier stars. These materials coalesced under the relentless pull of gravity, gradually forming a proto-solar nebula, a massive spinning disk that would eventually give birth to our sun and planets. In this early solar system, chaos reigned supreme. Countless collisions between emerging planetary bodies, known as planetesimals, were common, and these frequent impacts shaped the destinies of these celestial objects. Amidst this cosmic turmoil, Earth was just beginning to form. At that time, our planet was far from the hospitable blue world we know today. It was a seething, molten mass of rock and metal, subject to constant bombardment from comets, asteroids, and other protoplanetary debris. These impacts were not mere meteor showers. They were colossal events that could drastically alter the landscape, creating vast craters and spewing lava into the primordial sky. The young Earth, in this formative phase, was a dynamic and volatile environment, its surface a glowing sea of magma that bubbled and churned with the energy of countless collisions. The frequent impacts also contributed to the gradual accumulation of mass, helping the Earth grow larger and more defined over time. Chaotic environment. The early solar system was a place of rapid change and dramatic events. The proto-sun, in the center of this swirling maelstrom, had not yet ignited in nuclear fusion, but was gradually accumulating mass and pressure. Its gravitational influence began to organize the surrounding material into a more defined disk, where the process of planet formation continued. The smaller planetesimals collided and merged to form protoplanets, larger bodies that would eventually become the familiar planets we see today. These collisions and mergers were violent, shaping the structure and composition of the growing planets. The formation of Earth, like that of other planets, was a process marked by intense heat and pressure. As materials collided and accreted, the energy of these impacts generated significant heat, keeping the young Earth in a molten state. Over time, the heavier elements, such as iron and nickel, sank toward the center, forming a dense metallic core. Meanwhile, lighter elements remained near the surface, creating a primitive crust and mantle. This differentiation process was crucial as it laid the groundwork for the geological features and processes that would shape Earth's evolution. During this period, Earth's atmosphere was vastly different from what we experience today. It was likely composed of hydrogen, helium, and other volatile compounds, gradually accumulating from the surrounding nebula and outgassing from volcanic activity. The young Earth's magnetic field, generated by the churning molten metal in its core, began to form, providing some protection against the harsh solar wind and cosmic radiation that permeated the early solar system. In this dramatic and violent setting, Earth was on a path of growth and transformation, a path that would eventually lead to the formation of the Moon. The stage was set for a monumental event, one that would change the course of Earth's history and give rise to our closest celestial companion. This early chapter in the story of the solar system, characterized by chaos and creation, laid the foundation for the events that would follow, including the cataclysmic collision that would ultimately birth the Moon. The giant impact hypothesis. Enter Theia, a Mars-sized protoplanet whose destiny was intricately intertwined with that of the young Earth. According to the giant impact hypothesis, Theia was one of many large bodies orbiting the nascent Sun in the early solar system. This theory suggests that Theia was on a collision course with Earth, a fateful trajectory that would culminate in one of the most significant events in our planet's history. As Theia approached, the gravitational forces between the two bodies increased, pulling them together in a slow-motion collision that would unleash energies beyond human comprehension. When Theia finally collided with Earth, the impact was cataclysmic, transforming both bodies in an instant. The collision released an immense amount of energy, equivalent to billions of nuclear bombs detonating simultaneously. This energy vaporized Theia and a significant portion of Earth's outer layers, launching a vast amount of debris into space. The impact was so powerful that it liquefied rock and metal, creating a massive glowing cloud of molten material that surrounded the Earth. This cloud, composed of vaporized rock, dust, and gas, formed a ring of debris that began to orbit our planet. The impact was not merely a surface event. It penetrated deeply into both Earth and Theia, causing their materials to mix and merge. The heat generated by the collision was so intense that it likely melted the impacted regions of Earth, creating a magma ocean that covered much of the planet. This molten sea churned with volcanic activity as the material ejected into space began to cool and solidify. The debris cloud, initially a chaotic and expanding mass, gradually coalesced into a more organized structure under the influence of gravity. Over time, the particles in this debris cloud began to stick together, clumping into larger and larger masses. This process, known as accretion, was driven by the gravitational pull of the emerging moon. As these clumps grew, their gravitational forces increased, attracting more material and accelerating the process of formation. The early moon, still a molten and glowing body, gradually took shape as it accumulated more debris. The intense heat from the impact and subsequent collisions caused the moon to remain in a molten state for a considerable period, eventually cooling and solidifying as it settled into its orbit around Earth. The impact also had significant effects on Earth itself. The energy released from the collision altered the planet's rotation and axial tilt, creating the conditions for the complex climate patterns and seasons we experience today. The impact may have also contributed to the formation of Earth's core and mantle, as the mixing of materials from the Theia and Earth helped to differentiate these layers. This process of differentiation, where heavier elements sank to form the core and lighter elements formed the mantle and crust, was crucial in shaping the structure of our planet. The giant impact hypothesis provides a compelling explanation for the unique characteristics of the Moon. Its composition, which is strikingly similar to Earth's outer layers, suggests a shared origin from the materials ejected during the collision. The hypothesis also explains the Moon's relatively large size compared to Earth, as the massive amount of debris ejected into space allowed for the formation of a substantial satellite. This theory, supported by a wealth of geological and geochemical evidence, offers a dramatic and scientifically plausible narrative for the Moon's creation. Formation of the Moon. Over the course of millions of years, the debris ejected into space by the collision between Theia and Earth began to undergo a remarkable transformation. This debris, a chaotic mix of molten rock, metal, and gas, orbited Earth in a vast glowing ring. Under the influence of gravity, the particles in this ring began to collide and stick together, forming larger and larger clumps of material. This process of accretion, driven by the gravitational forces of the growing Moon, was a slow but steady progression towards the formation of a new celestial body. As the clumps of material continued to collide and merge, they formed larger and more cohesive masses. These masses, in turn, attracted more debris, growing in size and gravitational influence. The early Moon, still a molten and glowing body, gradually took shape as it accumulated more material. The intense heat from the impact and the subsequent collisions kept the Moon in a molten state for a significant period. This molten Moon, glowing with the heat of its formation, slowly began to cool and solidify over time. The process of cooling and solidification was not uniform, and the Moon's surface underwent significant changes as it cooled. Volcanic activity, driven by the heat of formation, created vast lava plains known as maria, which are still visible on the Moon's surface today. These maria, or seas, are dark basaltic plains that formed from ancient volcanic eruptions. The cooling process also led to the formation of the Moon's crust, a solid outer layer that began to develop as the molten material on the surface cooled and hardened. The gravitational forces between Earth and the newly forming Moon played a crucial role in shaping the Moon's orbit and structure. As the Moon grew in size, its gravitational pull influenced the material in the debris ring, causing it to coalesce more rapidly. The gravitational interactions between Earth and the Moon also helped to stabilize the Moon's orbit, gradually bringing it into the position we see today. This stable orbit allowed the Moon to continue growing and cooling, eventually becoming the solid rocky body that we observe in the night sky. The formation of the Moon from the debris of the Theia impact also explains many of its unique characteristics. The Moon's composition is remarkably similar to that of Earth's outer layers, as it was formed from the material ejected during the collision. This similarity in composition is evident in the isotopic ratios of elements such as oxygen, which are nearly identical in both the Moon and Earth's crust. This shared composition provides strong evidence for the giant impact hypothesis and suggests a common origin for both Earth and the Moon. The process of the Moon's formation also had significant implications for Earth. The gravitational pull of the Moon helped to stabilize Earth's axial tilt, which is responsible for the changing seasons we experience today. The Moon's presence also contributed to the tidal forces that affect Earth's oceans, creating the rhythmic rise and fall of tides that have influenced the development of life on our planet. The Moon's formation was not just a dramatic event in the history of the solar system, but also a crucial factor in the evolution of life on Earth. The Moon's surface, shaped by the process of its formation, bears the marks of its violent origins. Impact craters, created by the collisions of debris during the Moon's formation and subsequent impacts from asteroids and comets, cover its surface. These craters provide a record of the Moon's history, offering clues about the conditions and events that shaped its development. The Moon's surface also contains vast plains of volcanic rock, evidence of the intense volcanic activity that occurred during its early formation. The formation of the Moon from the debris of a colossal impact is a testament to the dynamic and violent processes that shape the solar system. It highlights the power of gravity and the importance of collisions in the formation and evolution of celestial bodies. The Moon, as a product of these processes, stands as a reminder of the dramatic events that have shaped our planet and the solar system as a whole. Evidence supporting the theory. The giant impact hypothesis, which posits that the Moon was formed from the debris of a colossal collision between Earth and a Mars-sized protoplanet, is supported by a wealth of scientific evidence. One of the most compelling sources of this evidence comes from the Moon rocks brought back to Earth by the Apollo missions in the late 1960s and early 1970s. These rocks, carefully collected and studied by scientists, have provided invaluable insights into the Moon's composition and origin. One of the key pieces of evidence supporting the giant impact hypothesis is the isotopic composition of the Moon rocks. Isotopes are variations of elements with different numbers of neutrons, and their ratios can provide important clues about the origins of the materials they compose. The isotopic ratios of elements such as oxygen in the moon rocks are nearly identical to those found in Earth's crust. This similarity suggests that the Moon and Earth share a common origin, as the material that formed the Moon was likely ejected from Earth's outer layers during the impact with the Ia. In addition to isotopic similarities, the Moon rocks also reveal important information about the Moon's formation and geological history. The rocks contain evidence of intense heating and rapid cooling, consistent with the processes that would occur during the formation of the Moon from a debris cloud. The presence of certain minerals and the structure of the rocks suggest that they were formed in a high-energy environment, such as the one created by a massive impact. These characteristics provide further support for the idea that the Moon was formed from material ejected during a cataclysmic collision. The analysis of the Moon rocks also reveals important differences between the Moon and Earth's composition. For example, the Moon has a lower proportion of volatile elements, such as water and certain gases, compared to Earth. This difference is consistent with the giant impact hypothesis, as the high temperatures generated by the impact would have caused many volatile elements to be lost to space. The remaining material, which formed the Moon, would be relatively depleted in these elements, explaining the differences in composition between the Moon and Earth. Further evidence for the giant impact hypothesis comes from the study of the Moon's orbit and its gravitational interactions with Earth. The Moon's relatively large size and mass, compared to other moons in the solar system, suggests that it formed through a unique and dramatic process. The dynamics of the Moon's orbit, including its distance from Earth and the way it affects Earth's rotation and axial tilt, are consistent with the idea that it was formed from a massive impact. The gravitational interactions between Earth and the Moon also help to explain the stability of the Moon's orbit and its gradual movement away from Earth over time. The geological features of the Moon's surface also provide important clues about its origin. The Moon's surface is covered with impact craters, evidence of the intense bombardment it experienced during its formation and early history. These craters, along with the vast plains of volcanic rock, suggest that the Moon's surface was shaped by both collisions and volcanic activity. The presence of maria, or dark basaltic plains, indicates that volcanic eruptions played a significant role in the Moon's geological history. These features are consistent with the processes described by the giant impact hypothesis, where the Moon's formation involved both accretion from debris and significant volcanic activity. In addition to the evidence from the Moon rocks and geological features, computer simulations and models of planetary formation also support the giant impact hypothesis. These models show that a collision between a Mars-sized body and the young Earth could produce the conditions necessary for the formation of the Moon. The simulations demonstrate how the impact would generate a debris cloud, which could then coalesce to form a large Moon with characteristics similar to those observed in our lunar neighbor. The convergence of evidence from multiple sources, including moon rocks, geological features, and computer models, provides strong support for the giant impact hypothesis. This theory offers a compelling explanation for the Moon's formation, highlighting the dramatic and dynamic processes that shape our solar system. The story of the Moon's origin, as revealed by this evidence, is a testament to the power of scientific inquiry and the ability of humans to uncover the mysteries of the cosmos. Finally, the Moon's creation is a story of cosmic collisions and celestial formations. This narrative, pieced together from scientific evidence and theoretical models, reveals a dramatic chapter in the history of our solar system. The moon, a constant companion in the night sky, stands as a testament to the dynamic and sometimes violent processes that shape celestial bodies and create the conditions for life as we know it. The giant impact hypothesis, supported by a wealth of geological and geochemical evidence, provides a vivid and scientifically plausible account of the moon's formation from the debris of a colossal collision. As we continue to explore the moon and unlock its secrets, we gain not only a deeper understanding of our closest celestial neighbor, but also insights into the history of our own planet and the solar system as a whole. The moon's formation is not just a story of destruction and creation. It is a window into the complex and interconnected processes that govern the universe. The evidence gathered from moon rocks, computer simulations, and geological studies helps to illuminate the moon's past and provides a roadmap for future exploration. The moon, with its serene beauty and silent presence, continues to captivate our imagination and inspire our curiosity. Its story, as revealed by science, is a reminder of the incredible forces that shape our world and the cosmos. So, the next time you gaze at the moon, let your mind wander back to the dramatic events that forged its existence. Remember the colossal collision, the swirling debris, and the slow, steady process of formation that created the moon we see today. If you enjoyed this video, don't forget to smash that like button and subscribe for more fascinating content. We have only scratched the surface of the mysteries that await us in the universe, and there is so much more to explore.